Welcome back, students. So we have been studying the course optics, and we are talking about the first unit, that is the interference. And in interference we came to know the basic definitions. For example, wavelength, it is the difference between the two consecutive maxima crest or the trough. We also came to know the path difference. We also came to know the phase difference. And the relation between the path difference and the phase difference. So it is the 2 pi by lambda times path difference. This is equal to phase difference. Alright. We also came to know that what is the essential condition for a good interference pattern to take place, and that is the coherence. By coherence I mean the sources should be made up of or outcome of the original source, one parent source. For example, in Young's double slit experiment, source S, and we have a board and two pinholes S1 and S2. So these two sources are originated from a single source S, and they should have a constant path difference or the phase difference. It's like this is the first source S1, and let us say this is the second source S2. So they have a fixed path difference. It is not changing with time, and these are monochromatic sources, and there is no disturbance in these signals. It's like it will go in this way, so nowhere the signal is missing. If the signal is from this point, it is started like that, then the coherence is breaking. Okay, so today let us move ahead and talk about the famous Young's double slit experiment. So as the name suggests, it is a double slit experiment. For example, you have a source S here and the two pinholes acting as S1 and S2, two sources, and on the screen you are getting maximas and the minima. So this is the interference by division of wavefront. So source S is a coherent source. S1 and S2 are coherent sources. So the wavefront will be like that, and from this point there is upper half of the wavefront, there is lower half of the wavefront. So this is division of wavefront. Wavefront is getting divided into the upper half and then the lower half. So at any point P from these source S1 and S2, let us say here, so this is the path and this is the path. So we are going to calculate the path difference between the two, so S1P and S2P. So the path difference will be S2P minus S1P. So this will be calculating. So now let us do the mathematical derivation of these sources, and let us say Y1 is the first source. From S1 it is A sine omega t. This is the wave eliminated from source S1, A sine omega t. A is the amplitude, omega is the angular frequency, t is the time period. So it is continuous wave, so t is from minus infinity to plus infinity. It is always there. Your second source Y2 equal to, let us say, B sine omega t plus phi. So we have the second source having amplitude B, angular frequency omega, and phase phi. So this is the difference between the first source and the second source in terms of phase. So this full quantity is phase, this is amplitude, A and B are amplitude, this is phase. So you can see that with the difference between omega t and omega t plus phi is phi. So here phi is the phase difference. So as you know, interference is the superposition of the two sources y1 plus y2. So now let us add these two quantities. It will become A sin omega t plus B sin omega t plus phi. So you can expand sin A plus B. So I'll write A sin omega t as it is plus B sin A plus B. So it will become sin omega t cos phi plus B sin phi cos omega t. So we have just expanded the sin A plus B formula here. Okay, so it will become, alright, so I can write, so sin omega t term is here, sin omega t term is here. So I'll take common, it will become A plus B cos phi times sin omega t plus B sin phi, in fact I'll write, okay, sin phi cos omega t. This is y. The superposition of the two sources y1 and y2. So for the sake of simplicity, let us write this quantity A plus B cos phi. Let us write this because it is having sine term. So let us write it as R cos phi. And we have another term here, B sin phi equal to R sin phi. So we have written these terms for some reason and will make use of these expression into the original y. So y equal to, so if I write this term over here, so this expression becomes R times cos phi sin omega t plus R sin phi cos omega t, and it can be written as R, so it is sin A plus B only, sin omega t plus phi. So this is y. So now here the only thing which is to be known here is R. Okay, so we have two expression y equal to R sin omega t plus phi, and two more expressions, A plus B cos phi equal to R cos phi, and B sin phi equal to R sin phi. So to get R out of these two expressions, what I'll do, I'll square and add. So if I square, it will become A plus B cos phi square plus B square sin square phi, and if you add these two, R square cos square phi plus R square sin square phi, so it will be simply R square. So now if I expand this square, it will be A square plus B square cos square phi plus 2AB cos phi plus b square sine square phi equal to r square. So now in this expression, if I add these two quantities, it will become a square plus b square, because cos square plus sine square equal to 1 plus 2 times ab cos phi. This equal to r square. So this is the expression for r square. So now let us talk about the phi, because here this phi will decide this full expression. So let us talk about case 1, when phi equal to, so this cos phi has to be 0. So cos phi is 0 at phi equal to pi. Okay, let us see. Okay, so let us talk about the cos profile, because cos is going this way, and at 0 it is 1, at pi by 2 it is 0, and at 3 pi by 2 it is, I'm sorry, this is 0, this is pi by 2, this is 3 pi by 2, no, this is pi, this is 3 pi by 2, this is 2 pi. So add 0, 2 pi, so phi equal to 0, 2 pi, 4 pi, 6 pi. At these all pi values, this cos quantity is 1. So cos phi will be 1. So r square will become a square plus a plus b all square. And the values, for example, let us say talk about the second case. Okay, so we have r square equal to a square plus b square plus 2ab cos phi. So at phi value equal to pi by 2, 3 pi by 2, 5 pi by 2. At these value phi equal to 0. So the r square will be a square plus b square. And at phi values equal to pi, 3 pi, 5 pi, this r square will be a square plus b square minus 2ab. So it will be simply a square minus a minus b square, so r square. So the square can be removed. So for maxima, y equal to r sine omega t plus phi. So for the maxima, r equal to a plus b. So for a good interference pattern, as you know, the amplitude of the first source is equal to the second source. So a will be b. So from here you can see it will represent 0, and from here it will to a. So I can write y for the maxima as, this is amplitude, the square will be 4a square sine omega t plus phi. So this is the amplitude of the resultant wave. If I want to plot it, I can write it in this form: y equal to 4a square sine omega t plus phi. So it will be like that. So 4a square is so this will be intensity I. So when I plot this, it will be like that. So it will not cross the zero line. This is zero line, for example. So it is 4a square. This is y-axis. So this is 4a square. And these are minima at these values when phi value is satisfying in such a way that it will give you minima. So this source F in double slit experiment is basically having in Young's double slit experiment the two sources S1 and S2, and at any point P on the screen what will be like that. So S1P and S2P are the path differences. So this is the distance between the two sources, small d, and this is capital D is the distance between the source and the screen. So what I'll do, I'll calculate the path difference. So it is like that. These are the two sources and this is the point P. This is small d here and this is the axial line. This is y, let us say, from this point P. So P is any point and you can write it anywhere. You can have anywhere this point. So we have two sources S1 and S2. So let us calculate the path difference between the two sources S2P. So S2P square minus S1P square. So I'll apply Pythagoras here. So this is the hypotenuse. So the base square plus perpendicular square. So this will be for S2P, it will be d square. This is capital D square plus y plus d by 2, because this is for this triangle, this is the additional length which is d by 2, y plus d by 2 square minus this d square plus, so I'll write bracket for this, y minus d by 2 square. So this, you know, it will become a plus b square minus a minus b square is equal to 4ab, 4 times yd. So it is 2 here, so it will become 2yd. So this is s square minus p square. It can be written as because S1P and S2P are nearly equal, so it can be written as S1P plus S2P times S1P minus S2P. It is just a plus b, a square plus b square equal to a plus b times a minus b. So if I take this in the numerator, in fact denominator, I can write 2y upon times d divided by, so S1P plus S2P. So S1P plus S2P can be taken nearly equal to d. So d plus d equal to d. So it will become 2 capital D. This equal to S1P minus S2P. So this is the path difference, yd upon capital D. So when this path difference equal to n lambda, integral multiple of wavelength, we'll get a maxima. So for this y will be n lambda capital D upon small d. So this is the expression for the maxima. Likewise, we have the expression for the minima. y small d equals upon capital D. This is the part difference when this part difference is half integral multiple of wavelength. So for this you will get a minimum. So you can find y here 2n minus 1 lambda capital D upon small d and 2 also. So at this value of y on the screen from the axial point, this is the y from any point P. From this axial point, this is any point P. So this point P can be anywhere. So y value will be different. So whenever the y value will be this much, you will get minima, and y value equal to n lambda capital D upon small d, you will get a maxima. So y will get a maxima, and y will you get a minima. So when the path difference is integral multiple of wavelength, let us say this is the first source and this is the second source. So this source, these two sources having lambda path difference. So you can see the maxima is on maxima, minima is on the minima, maxima is on the maxima. So you will get constructive interference and you will get maxima. And when the path difference is half integral multiple of wavelength, so this is the starting point, this is the first wave, and this is the starting point, this is the second wave. So first lambda by 2 basically path difference. So it will be like that. So at minima there is maxima, at minima there will be at maxima there will be minima, at maxima there is minima. So the path difference condition is so satisfied that they are cancelling their effect. Alright, so this we have also seen from the phi value. When phi value equal to 0, 2 pi and 4 pi, you are getting a maxima. When phi equal to pi, 3 pi and 5 pi, you are getting maxima. And phi value equal to pi by 2, 3 pi by 2 and 5 pi by 2, you are getting minima. Okay, fine. So now let's talk about the fringe width. Fringe width. What you'll see on the screen is the maxima and the minima, and you're seeing that y equal to y small d equal to n lambda. This is the path difference and equal to n lambda. So the distance between this, so y is basically any point on the screen P, and this is y. So the difference between the two maxima will be the fringe width. ये आ रहा है ना, तो इसमें और इसके बीच का जो डिफरेंस है, दिस इज कॉल्ड फ्रिंज विड्थ. और द डिफरेंस बिटवीन टू मिनिमा वी कैन आल्सो टेक इट इन दिस वे. जैसे वेवलेंथ में हम बात करते हैं, you can take either quantity. So this will become, so I can write y equal to n lambda capital D upon small d. So y1 is for the n equal 1, y1 equal to lambda capital D upon small d. y2 can also be written as 2 lambda capital D upon small d. So the difference between y2 and y1 is fringe width beta equal to, say if you subtract, you can write lambda capital D upon small d. So this is fringe width. You can do this exercise for 2n minus 1 by 2 lambda. This is for the minima. So it can be seen that on the screen the fringe width is directly proportional to wavelength. Higher is the wavelength, you will get, for example, for the red color you will get a maximum fringe width. The distance between the source and the screen, larger is that distance, you will get wider fringe width, and smaller is the value of the two pinholes, you will get broad fringe width. So this fringe width is basically the difference between this point and that point. So this bright region, this is the fringe width. So this will be wider if you have larger wavelength, narrower if you have smaller wavelength. So these many factors decide whether the value of this fringe width will be larger, smaller. Okay, thank you.